Hello, guys. You're welcome to this lecture on introductory abstract algebra. In the past couple of weeks, we've looked at groups. Now we want to look at rings, understand what rings are. Okay, so let me just expand my screen here. Okay, so I'll give an introduction, and then we'll define what a ring is and go through a couple of interesting examples of what rings are. And then in subsequent videos, I will do properties of rings, a famous theorem on rings, basically on multiplication. Then we'll look at ring homomorphisms and isomorphisms, similar to what we did in groups. And then we'll look at subrings and then fields. Okay, fields are basically type of rings, if you like. Okay, so in talking about groups, if you remember, we said a group is basically a set on which you define a binary operation, let's say star, and then it satisfies like three axioms, right? Associativity, the set must have an identity element, and if you pick any element in the set, that element must have an inverse. Okay, so if these are satisfied, you call that a group. But there was only one binary operation. So that is a distinctive feature of groups. So in the next couple of slides, we want to talk about rings where instead of just having a single binary operation, we're going to have two of them, basically addition and multiplication. Okay. That's because, there are many sets that are equipped with both addition and multiplication, and that makes it interesting in solving problems, polynomials, linear equations, and all of that. Okay, so rings, if you like, they are more, say, practical, right, than groups, because you have both addition and multiplication defined on them. But also you're going to have more axioms to deal with. So that makes them a bit more complicated than groups, right? Because they are basically groups plus, right? Groups in terms of addition plus other things. And so that makes it a bit more complicated. But basically a group is a binary structure on which you have two binary operations, right? You have a set with two binary operations defined on it, then you call that a ring. So I'll give you a formal definition of what a ring is. Here it is. So basically, a ring, right, is a set here, R, right, with the operations of addition and multiplication, and for which these axioms are satisfied. This R with the addition has to be an abelian group, okay? So if this is an abelian group, and for every element in R, you have multiplicative associativity, okay? And for all A, B, and C in R, you have left distribution law holding. You have A multiplied by A plus B plus C can be written as this, right? we know this already, right? A times B plus A times C. And you can do that for the right side as well, right? A times C plus B times C. Okay, so basically, these three axioms, you can expand them to be more, if you like, right? So these axioms must be satisfied for you to call this structure a ring. Okay. If any of them, right, is violated, right, any one of them is violated, you can call the structure a ring. So that is important to take note of that. Okay. So note that we could have, in some text, you would have this expanded to be more, right? This would be expanded to be to have more axioms instead of just three, right? Because to say that it is an abelian group means that, number one, right, you have associativity in terms of addition, right? So associativity with regard to addition. To say that it's an abelian group also means that you have for the set R, there has to be, if you like, an identity element belonging to R, right? Such that, I mean, if you take an element in R, plus, in this case, plus E plus X must be equal to X, right? So there has to be an identity element. C, if I pick any element X in R, that element must have an additive inverse, right? So in this case, a negative of that, right? Plus X, and that will give me my my identity. Well, the identity is 0 in this case, right? So this E is basically 0. And then because it has to be an abelian group, you also need additive commutativity, right? So D, you need, if I take X plus Y, this has to be equal to Y plus X, right? So point 1 alone, right? If you like, condition 1 alone can be split into 4, all right? Plus these other ones. So there are more axioms. So saying that R is an abelian group basically means these have to be satisfied in terms of addition. You need multiplicative associativity, and you need these ones to be satisfied. So to show that, for the most part, right? For the most part, to show that a structure is a ring, you need to go through these axioms. So that is why you need to understand this very well, understand this definition, and know that definition, right? To help you to be able to prove that something is a ring. Of course, sometimes you have theorems, right? That will give you a shortcut, if you like, approach to proving these things. But for the most part, this is what you need to show, right? That the structure is a ring. So keep this in mind. I'll probably come back to this again. Okay, good. So these are some examples of rings. A set of integers with addition and multiplication defined on them or on it. The set of rational numbers, the set of real numbers, the set of complex numbers. Okay, so you see that these are like infinite rings because R, Z, Q, and C, these are infinite sets, right? But what is common is that both of them must have addition and multiplication defined on them. G here, which is just the set with the 0 element, is called the trivial ring or the 0 ring. Okay, I'll come back to this later on before we introduce fields. Okay, but the task for you is to actually take this and actually show that it is a ring. So first, show that it is an abelian group, right? A set with only 0. And then show that there is multiplicative associativity, show that the left and the right distributive laws hold. Okay, once you're able to show that, then you have shown that this is actually a ring. So show that the 0 ring is a ring. That's a task for you, okay? A more interesting example is the set of functions, right? Let's call it F. Where any function here will take elements from R to R. R is a set of real numbers. And on this, we've seen this example before. We define addition by this, right? F plus G of X will be equal to F of X plus G of X, where F and G are functions, right? They are in F. X is real, and their multiplication is defined by this, okay? So with these definitions, we can actually show that this guy here is a group. We've done this before in dealing with groups. So we've shown that it's a group. So the only thing we need to show here is that it's an abelian group in terms of addition, so that F plus G must be equal to G plus F. Okay, once that is done, then we know it's an abelian group, and then we have to show the other 3 conditions, right, to show that it is a ring, right? The set F here, the set of functions defined by this ring. So for abelian or additive commutativity, we have this, right? F plus G of X is equal to what? Is equal to F of X plus G of X. We know this. Well, this is a function of X, and that's a function of X. For functions, right, we can basically rewrite this as G of X plus F of X. Okay. And this, of course, we can also write it in this form, which means that F plus G is equal to G plus F. That shows that this structure here, in terms of addition, is an abelian group. Okay, good. So that is the first axiom, if you like, for to show that something is a ring. The next is to show that there is multiplicative associativity, right? Well, we defined multiplication by this. I've already shown this actually. So we define it by this. Then, of course, once we define it by that, then fg times h here multiplied by x means I can distribute x here on h as well as on this product, right? I can rewrite as this. Well, this fg times x can also be written as this, right? F of x times g of x. And of course, I can rewrite this as this, okay, which I can rewrite as that. I can pull out the x, and then I can pull out the x from this and that. Therefore, fg times h is equal to g f of g, right? So this shows that multiplication is associative. Basically, that is. So that is the next axiom. Axiom number 2 is satisfied, okay? Then we show, we're going to show the left distributive law, and then your task is to try it for the right distributive law. So for the left one, I take f multiplied by g plus h on x. I distribute this. So I'm going to have f of x, g plus h of x, and this will be equal to f of x. Okay, I can rewrite this as that. While in terms of multiplication, this is now straightforward. F of x, g of x, h of x are all functions of x, right? So we can rewrite, we can multiply them, multiply this by that and this by this, right? And then, of course, this is the same as that, and this is the same as that. I can pull out the x and I have this. So basically showing that f into g plus h is equal to f of g multiplied plus f of h, right? And that is the left distributive law. So the left distributive law holds. So you can check that. You can follow a similar approach to check that the right distributive law holds. So it is the set of functions with those definitions is an abelian group. We show that it's a multiplicative, multiplication is associative. We've shown that there's left distribution. You show that it is right distribution. And then, so with this, you can conclude that it is a ring. Okay, good. So that is how you show that something, a structure is a ring. Okay, so now keep in mind, okay, keep in mind that from the definition of a ring, right? From the definition of a ring, that a ring is more than just a group with, let's say, with multiplication defined on it. Okay, it's more than that. Okay. Also note that do not assume that a ring has a multiplicative identity. Okay, it does not need to have a multiplicative identity. In the definition, nothing says anything about multiplicative identity. If you go back here, all we want is that multiplication must be associative. There is nothing about multiplicative identity. Okay, so I don't need to have an element, let's call it E, such that when I multiply it by some X in R, all right, I get X. Okay, I don't need to have that. There are some rings which have multiplicative identities, but in general, you don't need multiplicative identity, all right, to have a ring. Also, you don't need to have a multiplicative inverse, okay? So if I have X being an element of R, not R as a ring, okay? An element of the ring R, I don't need to have X inverse or 1 over X to be the inverse of it, right? And that makes sense because if I'm not requiring a multiplicative identity, of course, I can't require a multiplicative inverse because when I take the inverse multiplied by the element, what I need to have is the identity. But I don't need the identity, so I don't also need a multiplicative inverse to have a ring. Okay, so this definition does not say anything about having a multiplicative identity or a ring in the set, multiplicative ring. Did I say multiplicative ring? Multiplicative identity and a multiplicative inverse. Okay, inverse. Okay, good. So keep that in mind. That is very important. You need these things with addition, but not with multiplication. Okay. So you should be mindful of that. So okay, back to the warning here. So a ring does not need to have a multiplicative commutativity. Good. Neither do you need to have multiplicative commutativity. In other words, A multiplied by B does not necessarily be equal to B times A. Okay, I don't need to have this in order to have a ring. Okay, if that happens, if that holds, if AB is the same as BA, then you say that the ring is commutative. But that is a special type of ring. We'll come